Welcome to Friday Math Happy Hour. Today, I'm going to go over possible questions for exam 2 review. As an instructor, this is the type of questions that I actually gave on exam number 2. Okay, so let me see which questions I'm going to cover. So the topics covered are sections 4.1, 4.2, all the way to 4.4, which is exponential and logarithmic functions. And also the mathematics, finance, which is chapter 5, 5.1, 5.2, 5.3, and 5.4. I believe I have about 20 questions or 20 problems that I'm going to help you work out. Okay, so to begin, let's start with topic number 1, which is section 4.1, graphing exponential functions. Okay, now when graphing exponential functions, such as f of x equals to 2x, recall when I gave this topic, about 2 weeks ago, 3 weeks ago? The best thing is to select points. And the points that is wise to select is -2 to about 3. Okay, so let's draw ourselves a little table. These are my x values. F of x means these are also my y values. F of x is a function when y. F of x and y are the same thing, because when y is a function, then we can write it as f of x or y. So let me start with the points. So when x is -2, we're going to plug in -2. We're going to evaluate the function f of -2, which means I'm going to plug in -2 for every x. So this becomes 1 over 2 squared, which is 1/4. So when x is -2, y is 1/4. When x is 1, right, we repeat the process. So it's going to be 2 to the -1, which is equal to 1 over 2 to the first power, which is equal to 1/2. So when x is -1, y is 1/2. Now let's evaluate f of 0. So we're going to plug in 0 for where the x is. So anything to a 0 power is always 1. So when x is 0, y is 1. Now let's see what happens when x is 1. So we're going to evaluate f of 1, which means 2 to the first power equals 2. So when x is 1, y is 2. In a similar fashion, we're going to evaluate at 2, which would be 4, because 2 squared is 4. So when x is 2, y is 4. And lastly, when x is 3, we evaluate f of 3, which is equal to 2 cubed, which is equal to 8. So when x is 3, y is 8. So now this is my graph. And all these points, for example, -2, 1/4 is about here. -2, right? So 1/4 means that you're going to cut the first unit from 0 to 1 into 4 equal places. So that's why it's about right there. That's about 1/4. When x is -1, this is -1, so y is going to be about 1/2. Then when x is 0, it's going to be 1. When x is 1, if you notice, it's going to be 2. When x is 2, y is going to be 4. And when x is 3, y is going to be 8. So that's my graph. Okay? Okay, now let's graph another one. Hey guys, this graph here is going to be like a horizontal shift to the right. So all these points are going to move one to the right. Okay, but how do we graph it? So let's graph it by using the same points. Here's my table, and I'm going to use the same points, right? -2 all the way, but this time all the way to 4. So again, the same process, right? I'm going to plug in -2 here, where the x is. So -2 minus 1 will give us -3. So 2 to a -3 will give us 1 over 2 cubed, which will give us 1 over 8. So when x is -2, y is 1/8. And similar fashion, when it's -1, we're going to evaluate it from -1, right? Which will equal 2 to the -2nd power, which is equal to 1 over 2 squared, which is 1/4. When it's 0, so 0 minus 1 is equal to -1. And 2 to the negative first power will give us 1 over 2, which is 1/2. When x is 1, and we plug in 1 here, right, for the x's, it's going to give us 1 minus 1, which is equal to 2 to the 0 power. And like I mentioned earlier, anything to a 0 power will always be 1. So when x is 1, y is 1. When x is 2, right, we do the same process. So it's going to give us 2. When x is 2, y is 2. When x is 3, again, repeat the process. Y equals 4. So when x is 3, y is 4. And lastly, again, when x is 4, we evaluate at 4, which is 4 minus 2 to the 4 minus 1, which will give us 2 to the third power, which is equal to 8. So when x is 4, y is 8. And here's my graph. And again, all these points are the points here in this graph. So for example, -2, right? This is -2. It means that we cut this. This is right. This is 1 here. We cut this unit into 8 equal parts. So that's why -2 will be about right there. And then when it's 0, right? 0 will be 1/2. When it's 1, it's going to be 1. When it's 2, y will be 2. When it's 3, y will be 4. And when x is 4, y will be 8. So that's my graph. Okay. Now let's graph one more. Every graph that I'm showing you guys is a little bit different. 2 to a negative x, and again, I mean g of 2 to a negative x is the same thing as 1 over 2 to the x power, which is the same thing as 1/2 to the x power. So again, if we're going to graph this graph, right? So we're going to plug in the values for x. So we choose the same values, or -3 to 3, and these are my results. Okay, and here's how we do it. When x is -3, I'm going to plug in -3 for the x. That means when it's negative, right, we use a reciprocal and make it positive, and it becomes positive. I mean, we use a reciprocal of 1/2, which is 2 over 1, and then the exponent becomes positive, which is equal to 8. And then we repeat the process, right? So all these, right, so we're going to plug in all these numbers here from -2 to 3. If we repeat the process, this is what we get here, guys. Let me go back real quick. We get all these answers here. And this is my graph. Okay, so to select key points, right, when it's -3, it's going to be 8. When it's -2, it's going to be 4. When it's -1, y is 2. You see, it matches the points over here. When x is 0, y is 1. When x is 1, it's going to be 1/2. When x is 2, 1/4. When x is 3, 1/8. If you notice, if we keep going on the positive x values here, it's going to get closer and closer and closer to the x-axis, but it will never reach it. So that's why it's useless to keep using more points. Towards the positive side. Okay. So this is a graph for the function g of x equals 2 to the negative x power. Okay. Let's continue. Now, how do we use this like in real life? Okay, here's an example. Number 4 here. The assets in billions of dollars for Prudential Financial Incorporated can be approximated by the function a of x equals to 315 e to the 0.05x to the 0.056x, where x equals 7 corresponds to the year 2007. Find the assets for the following years. So solution. So since x equals 7 corresponds to the year 2007, so then x equals 0 must correspond to the year 2000. And x equals 12 corresponds to the year 2012. Okay? So then all it means that to evaluate a, right, at 2000, I'm going to plug in 0 for the x. We're going to evaluate a of 0, which means I'm going to plug in 0 for the x. So this becomes 315 e to the 0 power. Anything to the 0 power is 1. So the answer will be 315, right? But it's in billions of dollars. So it's 315 billion. Okay, now it's good to know, guys, that 315 is the initial value because time is 0, right? So when t is 0, This is the initial value. This is useful to know for the next problem that we're going to do. Okay, but let's continue with B. We're going to evaluate A at 12 again, which means I'm going to plug in 12 for the x. So here, guys, you have to be careful. Make sure in the calculator that you put parentheses for the exponent, and you put 0.056 times 12 and then close parentheses. Because if you don't do that, it might give you the wrong answer. Why? Because the calculator follows PEMDAS. And if you do it like, just a way like this without the parentheses, it might do 315 e to the 0.056, and then that times 12, which is wrong. That's why it's wiser to put it in parentheses to make sure that your answer will always be right. Okay? So if we do that, we should get something like 616.817155. Round it off to the 10th place. So it's going to be $6.8 billion approximately. Okay, now this is number 5. Hey guys, if you have any questions in the meantime, just put them in the chat, and the moderator will stop me, and that way I can answer your questions. Okay, or else you can wait till the end. It's up to you. But you're welcome to stop me. At any time. Number 5. I like to use an example because this was right before COVID started. So that's why I wanted to use an example. So for students to know how important it is to know how to use exponential functions. Okay. So this is more or less some of the information that I got at the time that it just happened. So for example, a deadly virus has infected the world. At the end of January, there were 2 cases, and by the end of April, the cases had grown to 128. So A part, find a model of the form f of t equals to y naught, b to the t power, with t equals 0 corresponds to the end of the month of January. And then B, if the trend continues, how many people will be infected by the end of the year? Okay, so here, guys, the solution is for part A, I need to find my y naught and my b, right, and plug it into the formula. This way I have the model. So here, y naught is the amount present at time equals 0, or when the virus just started. So if we go back and read it, a deadly virus has infected the world at the end of January, right? There were 2 cases. So y naught is going to be 2. Because since t, right, when it just started, t equals 0 corresponds to the end of January, which there were 2 cases. Then y naught equals 2. So then I use the other information that by the end of April, the cases had grown to 128. So with that, I need to find my b. Okay? So when t equals 2 corresponds to the end of March, because when t was 0 corresponded to the end of January. So t1 corresponds to the end of February, t equals 2 corresponds to the end of March, and t equals 3 corresponds to the end of April. So this is what we need. So at the end of April, there were 128 cases, right? It says here on the introduction of this problem here. So then we can go from t equals 0 to t equals 3. So then we use what we know to find b. So here's my formula: f of t equals y naught b to the t. So we're looking for b, right? So this is what we know. In 3 months, right, from when it started, there were 128 cases. And y naught equals to 2. So I'm going to plug in the 2 for y naught. I'm going to plug in the 128 for f of 3. Right, so f of 3 is 128. That means when t equals 3. So that's why this is 128. And in 3 months, there were 128 cases. So that's why it's going to be 128 equals to 2 b to the 3rd power, right? This is a time in 3 months. There were 128 cases. So now I need to solve this for b. So I divide both sides by 2. So then 64 equals to b cubed. Now I'm going to raise both powers to the 1/3 power. So I can cancel the 3 there. So raise both sides to the 1/3 power. So b to the 3rd to the 1/3 power gives me 1. That's why this would just be b to the first power. And 64 to the 1/3 power will give you 4. If you plug this in the calculator just the way it is, it's going to give you 4. But make sure that since exponent is a fraction, make sure that you put it in parentheses. Okay, so b equals 4. So now I have my initial value and I have my b. Right, y naught is 2 and b equals 4. So I found my model. So y naught is 2 and b is 4. So this is the answer for A. F of t equals to 2, parentheses 4 to the t power. Now comes part B. So from January to December, it's going to be 11 months, right? Because it's saying that it's at the end of January is when it started. So then for B, we want to see by the end of the year. By the end of the year means by the end of December. So it's going to be 11. That means f of 11 is equal to 2 to the 4th power, right? To the power of 11. And all I did was plug in the values here. F of 11 is, the y naught was 2, my b was 4, and the t is 11. So this gives me, let's see, 838. There's going to be 8,388,608 people infected by the end of the year. I know there wasn't this many people infected. I mean, in reality, because there were like a lot of they did like a lot of mass mandates and all that stuff, which prevented the spread, the virus to spread if there was no if there was nothing holding it back. So, for example, if there were no maps, there was nothing that we did as a nation or as a population, then this would have been more or less like an accurate figure. Okay, but again, we intervened by using vaccines and other stuff. That's why it didn't reach that many people. But this is a good example of how you use exponential functions. Now, the next one that I'm going to cover is solving exponential equations. And I believe I did a PowerPoint on this one. So here, for this to work, okay, it says let A be a positive real number with A cannot equal 1. So this holds place. If A to the U equals A to the V, then U must equal V. This holds true as long as the two bases are the same. Okay? So once the two bases are the same, we can apply the rule. For example, the two bases are the same, correct? So we apply the rule. So an x must equal to 5. Okay, now this is number 6 then. Are the bases the same? No, they're not, correct. Not the same base. So now, let's see if 25 can be simplified with a base of 5. 125. 125 is equal to 5 cubed. So we're gonna simplify 125 and replace it with 5 cubed, right? Which is the equivalent. So now here we're gonna apply the power rule, which means we multiply the exponents. So now 5 to the 3x equals to 5 to the 5th power. Now we have the same base. So now you can apply the rule. So 3x equals 5. We divide both sides by 3. So x equals 5 over 3. And all these can actually, you can check your work. Okay, you can always check your solution. So I'm going to plug in 5/3, right, for the x. So you can plug in the calculator, but remember what I mentioned earlier, every time they're going to plug in a fraction as an exponent in the calculator, make sure that you put it in parentheses. So you see, so this is the same thing, guys. So I know this is a correct answer. Okay? Solving exponential equations, continue. Now again, we're trying to make it with the same base, right? So I know that let's try with 4. Let's see if 4 to a power will give me 32. Right? Not the same base. So 4 squared will give me 16, right? It's not 32. So let's try 4 cubed. 4 cubed is 64, right? So 64 is too much, which means I have to simplify or change both bases to make them the same. So perhaps we can use 2. The common base between 4 and 32 is going to be 2. Because 4 is equal to 2 squared. And 32 equals, I believe, 2 to the 5th power. So then 4 is equal to 2 squared. Bring down the x minus 1. And 32 is the same thing as 2 to the 5th power. So again, here, guys, I'm going to apply the power rule, the exponent power rule, which means I'm going to multiply the exponent. So this becomes 2 to the 2 parentheses x minus 1 equals to 2 to the 5th. Now they get the same base. Now we can apply the rule. The rule means that since they have the same base, then the exponents must equal to each other. We're going to distribute. It'll be 2x minus 2 equals 5. We're going to add 2 to both sides. So 2x equals 7. We're going to divide both sides by 2. X equals 7 over 2. And again, we can always check our work. So let's check it. X was 7 over 2, so I'm going to plug in 7 over 2 for the x's. So 7 has minus 1, I believe is going to give us 5 over 2. Now all we do is put it in the calculator, right? So if we put 4 to the power of 5 divided by 2, it's going to give us 32, which is correct. That's how you can check your work. Okay, now the next topic is writing exponential equations into logarithmic equations and vice versa. So, definition of logarithms to the base a. Y equals to log a base a of x means a to the y equals x. This is a logarithmic form. This is exponential form. Okay, so for number 8, it says write each logarithmic equation into an exponential. So here, guys, we have to know what the a is, right? So we want to go from logarithmic to exponential. So we have to know what the a, the x, and the y is. So my a is going to be 9. My x is going to be 81. My y is going to be 2. So then it's going to be right. My a is 9. My y is 2. And my x is 81. That's how you write it from logarithmic to exponential. Now we're going to go the other way around. Write each exponential equation into a logarithmic equation. So we have to know what the a, right? What the a, what the y, and what the x are. Okay? So this is exponential form. This is logarithmic form. So my a is going to be 5. My y is going to be 3, and my x is going to be 125. So then this will be my y, right? So my y is 3, right? My y is 3, my a is 5, and my x is 125. Or you can have it log of base 5 of 125 equals 3. These are the same thing, right? I believe for the solutions in the back of the book, this is the way they want you to write it. But if you write it this way, it's not wrong. They're both correct. Okay. Are you guys okay up to this point? If you're okay, just put a yes in the chat, please. And then Patricia, would you let me know if somebody has any questions?
Yes, sir.
So okay, I can continue, right? I'm going to continue. Okay, now, how do we graph logarithmic functions? And again, in order to, we have to use what we just learned, converting logarithmic to exponential, right? In order to graph without a calculator, must convert logarithmic equations to an exponential equation. So this is a logarithmic, right? And this is the equivalence in exponential form. So y equals log of base 2 of x means it's going to be 2 to the y equals x. So I'm going to graph this function here. But what's different than graphing an exponential, it was 2 to the x power equals y, and this is reversed. So then we're going to plug in the values for y, not for x, because it's easier if we plug them into for y, because y is the exponent. Okay, now, okay, here we go up here, x equals to 2 to the y power. So when y is -2, right, Then x equals 2 to a negative 2, which is 1 over 2 squared, which is equal to 1/4. So I'm going to put all the answers here on the right? But how do I get these answers for x? Here it is. We're going to repeat the process because I don't want to do each one individually. So repeat the process. Now I'm going to plug in negative 1. So if I plug in negative 1 here where the y is, I'm going to get 1/2. Why? Because 2 to a negative 1 will give me 1 over 2, which is 1/2. And I just keep repeating the process. If I plug in 0 for x, 2 to the 0 is going to give me 1. If I plug in 1 for x, for y. I'm sorry about that. It's going to be 2 to the first power equals 2. If I plug in 2 for y, it's going to give me 4 because 2 squared is 4. If I plug in 3, right, for y, repeat the process, plug in 3 there, it's going to give me 8. So this is a graph that I'm looking at, this one here. This is the exponential in blue, and this is a 1 in red is my log. And here it is, right? Because when x is 1/4, it means that I'm going to cut from 0 to 1 to 1 in 4 places. So when x is 1/4, it'll be about right here. It's going to give us negative 2. When x is 1/2, it's going to give us negative 1. When x is 1, right, y is 0, and you can follow the rest of the points. And lastly, when it's 8, it's going to be give me 3 from the last one there. So this is my graph. And I believe this is the exponential I graphed it earlier, I think on the first or second slide. Okay. There's my exponential, and there's my log. Okay, now this is expanding or condensing logarithmic expressions. So we have to know some rules first, or some properties. These are the properties for logarithms. This is called the product rule, the quotient rule, and the power rule. For the product rule, right, this is called single log. I believe they call it single log in 1324, and they call it condensed in 1314. And this is called expanded form. Okay? And it's also the same thing for the natural logs. Okay, you see this is the product, the quotient, and the power. And again, right, when it's this is called single natural log, expanded. So when you're multiplying, right, you expand them and you add them. See? When you're dividing, you expand it by subtracting. And you notice the power, the R goes to the front. You see, the R went to the front. Same thing over here with the log. The R goes to the front. Okay, those are the rules that we need to know. So here we go. Write each expression as a sum and or difference of logarithms with all variables to the first degree, which means they don't want no powers. They want everything, all the exponents must go to the front. So for example here, right, so here, I like to put numbers on these right here. I like to call the product number 1, the quotient number 2, and the power number 3. So here's what I tell my students, hey guys, what do you think it is? Which rules are we going to be using? So this is going to be, right, which properties? It's going to be the product and the power, right? Because we have the product multiplying and we have exponents, the power. So then this is what I tell my students. Okay, we're going to need to add 3 separate logs because we have 1, 2, 3. Right here we have 2, right? We have x and y, so we separate them in 2 logs. If we had x, y, and z, then it'll be 3 logs, like 3 different logs. If we had x, y, z, w, then it's going to be 4. So the numbers that are here, guys, are the ones that we're going to expand them, the number of terms that are going to be expanded. So here we have 1, 2, 3 is going to be 3 different logs. Log of 5 plus log of x to the 4th power plus log of y to the 3rd power. So this covers, right, the product property. But now comes the exponent property because it says here without variables to the 1st degree. So all these must be to the 1st power. What does that mean? That we're going to apply the power property. The exponents must go to the front. Okay? Exponents go to the front. That one's okay because they have no exponent. The 4 goes to the front. the 3 goes to the front. There's my simplified version, or the expression being simplified. So this is my solution here, guys. Okay? Let's try another one. Again, those are the rules again. I like to put them there so we can see what we're doing here. So here, right, this is going to be the rules that we're going to apply here are going to be all 3 rules, right? Because here we have division, right, which is the quotient property. Here we have a power, which means the power property. And here we have the product, right, because this is multiplication here. So this one, we're going to apply all 3 rules. So what should we do first? So first, let's do the quotient rule, right? Which properties are present, right? So it's all 3. So here, let's do the quotient first. Quotient means subtract, right? So it's going to be log, right? If we're using the, right, it's like the one here. Log of base 10 of x minus, so log of the numerator minus the log of the denominator. So log of the numerator over the minus the log of the denominator. Okay? Now we're going to apply the product rule. Execute the power rule. Execute that one, right, with the product rule. For the product rule, we're going to be expanding them, but we're going to be adding. So we have 2 terms, 1, 2. We have the x and the y. Okay. Now, to finalize the answer, the exponent must go to the front. Execute the power property. The 2 goes to the front. So that's the simplified version of being single log to expanded form. Okay. Let's try one more. And again, I like to put the rules on the PowerPoint every time. That way we can see the rules. So now here, guys, they want you to do it. They want you to put it as a single log. So these are expanded. They want you to go the other way. They want you to condense it. So first of all, right, we know it's minus. So it's going to have the quotient property. And it has a number in the front, right? Number in the front means it's going to be also the power property. So here, which properties are present? So it's going to be the power and the quotient. So first, right, execute the power. The coefficient goes to the front, to the top here. The coefficient goes the other way, goes to the top. Now we apply the quotient rule. We write subtract because it's a quotient. So we're going to write it as a single log. So this is my numerator and this is my denominator. And we're done. That's the answer, guys. Let me go back. So this is the solution, guys. Okay. Are you guys okay? Can I move on?
Yes, sir. There's no questions.
Okay, thank you, Patricia. Okay, now, guys, solving logarithmic equations. Okay, to solve logarithmic equations, logarithmic and exponential equations, you need to know previous properties such as, right, the same properties as before. Okay, now, hey guys, here at times, right, students have a hard time trying to know what to do here. Hey guys, remember the ones that we solved earlier that we had to put them in the same base? Well, in reality, guys, there's another way to get the answer. We can use the power property. Solving by using the power property of natural log. So I want to bring down the x. So how do I do it? Is by taking the ln of both sides. Bring down the power exponent by taking the ln of both sides. So I'm going to put the ln on the left on both sides. So by the power property, the exponent goes to the front. Right, so the exponent goes to the front. Now we divide both sides by the ln of 6. Now this one we have to put in the calculator because it's going to be real complicated to do it by hand. At times it's impossible to do it by hand, guys, but you can approximate, but it's real complicated to do it by hand. So that's why I use your calculator. So that's my answer. Approximately says to round off, say to 4 places. So 2.3869. So that's my answer. Okay, now guys, like I always mentioned, like in the previous PowerPoint that I did on solving these, it's very important to know The ln of a number, for example, the ln of 6 is an actual value. It's a number. It's a value. So you cannot separate them. At times, the students think that the 6 is separate. Like they try to divide by 6, both sides, which is wrong. The ln of 6 is a whole number. It's together. It's like a value. If you plug in the calculator, the ln of 6 is going to give you a value. Okay, so the ln's and the number is a value. You cannot separate them. Okay. Okay, now let's solve logarithmic equations. So to solve these, right, it says let u, v, and a be positive real numbers with a cannot be 1. If you have the log of base a of u equals to the log of base a of v, then u must equal v. In other words, if you have the same logs with the same base, right, then u must equal to v. For example, in this case, we have the log a on both sides. So on number 15, right, if there's no base, it just means it's base 10, right? No base means they're all base 10. So we cannot apply the rule yet, right? We cannot apply the rule. Why not? Right? To apply the rule, the single logs must be on both sides of the equation, of the equal sign. This one's okay on the left, but the right, you don't have it as a single log. So for the right side, I got to apply the quotient property. Put it as a single log, right? This is my numerator, and that's my denominator. Now we have the same log and with the same base, so now we can apply the rule. So then x must equal to x plus 3 over x minus 1. Now here, there's different ways to get the answer. You can cross multiply, or you can multiply both sides by x minus 1. And here, guys, I use the cross multiplication. The x is the same thing as x over 1. So I'm going to multiply x times x minus 1 and 1 times x plus 3. Okay? So x times x minus 1 and 1 times x plus 3. Now here I'm going to distribute. It's going to give me x squared minus x equals to x plus 3. Now every time that we have an x squared, more likely we have to let it equal to 0. Okay? So set the equation equal to 0 on the right side. So the term x and 3 must go to the left by doing the opposite. Here I'm going to subtract negative x and minus 3 to both sides. So if we do that, here we're going to have x squared. Negative x minus x will give me negative 2x, and the negative 3 will just bring it down. And on the right side, they both, x minus x will be 0, and 3 minus 3 will be 0. Now you have to factor. Okay? And if you guys don't know how to factor, I believe I did a presentation on factoring. Okay? Factoring is crucial for all types of math because it's like solving for the x-intercepts and it has other values. In this case, we're solving for the logs. So then here, guys, we're going to apply the zero property theorem, which is set binomials equal to 0, both of them. So x minus 3 equals 0, or x plus 1 equals 0. Now all we do is solve for x. X equals 3 or x equals negative 1. So these are my two solutions, right? But we always have to check our work. Hey guys, you have to recall that the logs cannot be negative. So the logs cannot also be 0, because if you put in the calculator log of 0, it's going to give you undefined or something like that, or you plug in log of a negative number. So right away I know that negative 1 cannot be it. But let's pretend I didn't know that. Okay? So I plug him in there. You see, this is not defined because if you put that in the calculator, it's going to be not defined. But if I continue, this will be log of negative 1 equals to log of 2 minus log of negative 2. Then if you put log of 2 in the calculator, right, it's going to give you a solution. But if you put in minus log of negative 2, it's going to give you error, undefined. That's how you know that the logs must be more than 0. Okay? So that's not an answer. Now let's try x equals 3. So I'm going to plug in 3 for every x, which is there, here, and here. So we're going to get log of 3 equals to log of 6 minus log of 2. So here, guys, I can do it. We can put in the calculator, right? So that's my answer. Or here I can use the quotient rule, right? Condense it. So by using the quotient rule, or the quotient property, this will be my numerator, that'll be my denominator, right? By using the quotient property. What's 6 divided by 2? It's going to give us 3. So we know that both are equal to log of 3, which is true. So that's my solution. My solution was, let me go back, was only 3, not -1. Okay. Okay, now let's continue. Here we're solving in another form, okay? So we're going to apply this rule here. If a to the power of log a base 10 of u equals to u. In other words, if you have a log with a base, if you want to get rid of it, you raise it to whatever the base is, then this becomes a base, and that becomes your exponent, but you do it to both sides. For example, in this case, I'm trying to get rid of the log of 4, correct? So my base is 4. So I'm going to raise both powers, so let the expression on both sides of the equal sign be the exponent, which means let this be the exponent, and the base of the logarithmic be your base. So this becomes my base, but to both sides. Now by applying the rule up here, the left side, for a log of 4, right, that's equal to 1. So this one, all we do is bring down the 5x plus 6. See, apply the rule. 5x plus 6 equals to 4 squared, which is 16. 5x plus 6 equals to 16. We subtract 6 to both sides. Then we divide by 2. By 5, and the answer is 2. So x equals 2, and like I said, we can always check our work. I'm going to plug in 2 for the x. So 5 times 2 is 10. 10 plus 6 is 16. 4 log of base 4 of 16 equals 2. This is correct because this is how you read it. 4 to what power will give me 16? And the answer is 2. That's how you read logs. You ask yourself, 4 to what power will give me 16? And the answer is 2. Okay. So I know that's a correct answer. Now we're doing what I did last week, right? Now we're doing chapter 5. So I'm going to cover maybe like 3 problems from chapter 5, and I believe that's how long I'll have to do this PowerPoint. It's about an hour. So number 17, it says, Gabriel invested his summer earnings of $3,000 in a savings account for college. The account pays 1.5 simple interest. What will be the value of this account after 2 years? And how much interest did he earn? So recall from last week's workshop that this is a formula that we're going to be using. Okay, because we're looking, right, at simple interest. This is a simple interest formula. And we're looking for what's the future value in 2 years. And how much interest did he earn? So we have to know what the future value is, the present value, my interest rate, and my time. And remember, the time is always in years. So now, what will be the value in 2 years? So we're looking for the future value, right? So then the 3,000 is going to be the present value. The interest rate is going to be 1.5%, which is 0.015. And the time is 2 years. We plug them into the formula. My PV is 3,000. My R is 0.015. And my T, the time is 2. Use a calculator. So that's the answer, guys. So then in 2 years, you have $3,090. So then how much interest did Gabriel earn? So the interest will be my future value, which is what we just got, 3,090, minus what you invested, which was 3,000. So you made $90 in interest in 2 years. Okay, that's how you do these type of problems. And more than likely, this is I give this problem with that interest because now more than likely that's what they pay you now in the banks. I can recall back in the 1980s, 1990s when I was growing up that they used to pay about 8 or 9% interest, which was like almost 6-7 times more than what they do now. So back then it was a real good time to invest money. But back then, a lot of people didn't have a lot of money, right? So now this is like an actual that's how much they pay you, about 1.5, maybe 2% at the most, 2.5 or 3%. That's how high I've seen it. So the value of the account after 2 years is $3,090, and the interest earned is $90. Okay. Now compound interest. Now this is another formula, which is a compound. Here's what everything stands for. The future value stands for the future of the majority value, or the future value. The PV stands for principal, or what I like to say is present value. The R is the interest rate per period converted to decimal, from percent to decimal. The number of compounding periods per year is the M. And right now I want to show you a table what the M stands for every for every problem. Like there's a specific word that tells you what's the value for M, and the T is times in years, and the I is the interest rate per period, which is the R divided by M, and the N is the total number of payments, or the total number of compounded periods. Okay, compound the keywords. So if the word says yearly or annually, my M is equal to 1. If it says bi-yearly or semi-annually, my M is equal to 2. Quarterly is 4. Monthly is 12. Weekly is 52, because there's 52 weeks in a year. Daily it's 365 or 360, depending if the book says 360, well then use 360. If not, use 365. I repeat, if the book says to use 360 for daily, you use 360, but if it doesn't say nothing, then you use 365. And then compounded continuous without stop, it's a different formula. It'll be future value equals to present value, e to the power of RT. Now, compound interest can be used, okay, this is the use of compound interest. Compound interest can be used to invest a certain amount of money without depositing additional money. So example, you deposit $9,000 in an account at your bank that pays 2.5 interest semi-annually. How much money will be on your account after 10 years? This is like, again, this is actually like what they pay you at the moment about this time. So let's see here. That's my formula, but this one's easier to plug in the calculator. So, right, easier to input in the calculator. So I'm going to find all these values here, the FV, PV, the R, the M, the T, the I, and the N. So here, what are we looking for? How much money will be in the account after 10 years? So we're looking for the future value. So the 9,000 is going to be my present value. My interest rate is going to be 2.5%. Converted to decimal will be 0.025. The M, right, compounded, let's see, compounded, here's a word, semi-annually, which is 2. The time is 10. Now the I is going to be R divided by M. 0.025 divided by 2 is going to give me 0.0125. And the N is M times T. 2 times 10 is 20. So I have all the info to plug into the calculator with only one unknown. So there's my present value. There's my I, 0.0125, right, for the I. And my N is 20. You put it in the calculator just the way it is, and that's the answer. Right, but they always want you to round it out to a nearest penny, so this is my nearest penny, 0.33. So if the third digit to the right, the thousands place, if it's 5 or more, then you add 1 to where the hundreds place is. So this is how much money will be after 10 years, $11,538.34. In other words, what you made is like 2,000 and something in interest, right? We subtract the future value minus our present value. You'll be about $2,538.34. That's how much money you would make in interest in 10 years. Now, let's try number 19. This problem is used to future value of an ordinary annuity is to set up accounts to see how much money you can have at a certain amount of time. So for example, at the end of each quarter, a 50-year-old woman puts $1,200 in a retirement account that pays 7.2% compounded quarterly. And again, something like this, guys, is actually something not at the moment. maybe something like in the 90s or 80s, that was how much they were given. When she reaches 60, what will be the value in the account? How much interest will she earn? There's my formula, right? Different formula now. So again, we're looking for, let's see here. We're looking for the future value. So the payments are $1,200 a month. I mean, $1,200 every quarter. But first, let's find my interest rate, which is 7.2%, which means 0.072. Compounded quarterly means 4. M is 4. The time is, okay, here's the time. Let me go back. So at the end of each quarter, right? So she was 50, right? And when she reaches 60, so how much is from 50 to 60? That's why my time is going to be 10 years. Because 10 years, she's 50 at the moment, and she wants to, when she's 60, she wants to see how much money she has in the account. So the I is R, 0.072 divided by 4, which will give me something like 0.018, and the M times T is going to give me 40. So plug everything in the calculator, right, just the way it is. Now here I'm going to show you how to use a calculator without clearing or stopping one steady flow until you reach the answer. So here's what I'm going to do. I'm going to enter what's in the numerator just the way it is in the calculator. You see, I'm going to input parentheses 1 plus 0.018 to the 40th power minus 1. You should see something like 1.04, 1320138 on the screen. Then what's next is division, right? So you're going to hit the division key, right? So this is what it means up to this point, right? Now you're going to hit the division key, which means division, and this is what you see on your screen, right? You can see the answer. What answer is this answer here? So it's going to be this answer divided by 0.018, and then you enter it. And this is what you see on your screen, 57.85111.879. So this is what you're doing here. And then you're going to press times, right? Because times 1200. That's what you see on the screen after you press the times key. Enter 1200 because you're multiplying by 1200, and this is the answer. 69421.34255, which means run that out to your nearest penny. It's going to be 69,421 and 34 cents. So how much money did you invest? So there were 40 payments, right? So here's going to tell you how much interest she actually made. So this is a lot of money, right, to have in 10 years. But let me see how much money she invested. There's 40 payments, right? So she had 40 payments times 1,200 is 48,000. So in reality, guys, you see, the higher the interest that they give you, the more money you're going to make. So she made $21,421 of interest, which is very, very good. But like I'm saying, they don't offer those type of interest. They don't offer those anymore. So anyway, that's how much she had in 10 years, and $21,421 was from interest. Now, let me do the last problem here. We have 5 minutes. This is, like I said last week, this is what I like to tell my students, right? Because when I teach this chapter here, most of the other classes are engaged, even though some of them might not be engaged at the beginning, which at times some of the students are not engaged. But once we reach to chapter 5, everybody's engaged. Why? Because it's all about money. And then I tell my students at the beginning that this chapter will show you how to save money, how to make money, how to buy a house, how to buy a car, and stuff like that. So right away, students, I get their full attention. And this is an example that I got from a student. Okay, I believe she was going for engineering, and I asked her, hey, well, when you graduate, what kind of house do you want to buy? And then she said, I want to buy like a real nice house, right, at a real nice place. So I said to you about what type of mortgage or what the value of the house is a nice house for you. And she said something about her aunt had a real nice house that was really expensive, and I want something like that, she said. So she said that it was worth about $325,000. Okay, so that's why I made this problem here. Okay, now let's bring it to life now. Okay, say this is you here. Say you want to purchase a house for $325,000. Most of the times, all the interest rate, right, the are fixed for 30 years. And at times there's 20 and there's 15, but most of them are for 30 years. So in this case, it's 30 years, fixed rate at 3.9%. That's how much you pay in interest. What are your monthly payments and how much interest did you end up paying? Okay, so let's see how it is. So this is a different formula. So again, I need to find all these values, right? This is the present value. Why? Because you're asking for the money now. You're asking the bank for a loan to buy the house. So that's why it's called present value. You're trying to get a loan for that amount, $325,000 to purchase a house. So then, right? So then we're looking for the monthly payments, right? So then the loan, the present value of the loan was $325,000. The interest rate is 3.9%, right? Which will be 0.039. And the compounded will always be 12 because it's always monthly payments. The time is 30 years. So let's find my I, right? The I is R divided by 12, 0.039 divided by 12 will give us something like 0.00325. And the number of payments that you're going to be making are like 360 because 12 times 30 is 360. So these are the number of payments that you'll be making for that loan. Okay, so let's plug everything in. Now, if you notice, this is a little bit different now, right? Because now we're solving for the payment. So I'm going to show you again in the calculator without stopping or or losing the flow of the calculator. I'm going to show you how to get the answer. Okay, so I'm going to input my numerator here, just the way it is. 1 minus parentheses 1 plus 0.0325 plus parentheses to the power of negative 360. If you put that in, then the calculator is going to give you something like 0.689043691 on the screen. Then you're going to hit, right, the division key because you're going to be dividing. Then you should see this on the screen. This answer with a division, and you're going to enter what you're going to divide it by, which is 0.00325. Then you're going to enter. Then it's going to give you 212.0134431 on the screen, which means all this right side is 212 with those decimal places. Now here, you're going to press on the inverse key. The inverse key means that you're going to multiply by the inverse. By what inverse? By this inverse here. That's what you should see on your screen. Then you're going to enter the 325,000. And then this is what you see. So in other words, the payments are going to be $1,532.92. But this is only for the payment, right? But most of the times, the taxes for the house and also the insurance is included, right? So this payment, I mean the house, the taxes and the insurance is not included here, but you have to include them. So say there's going to be like another, let's play it safe, like another, let's say what, another $500 on top of that. So say you're looking at a payment of about $2,000 a month. Since you're going to school, right, and you want to graduate, and once you graduate, your plan is to having a lot of money, right, because you want to have a nice job, maybe like an engineer or whatever you're going for. So more likely, engineers make about $70,000 to $80,000 a year, I think, to start off, or something in that area. So more likely, they can afford these payments, especially if both couple are working. Okay. So then, but let's see how much you actually paid for the house, right? It was $325,000. So then there was 360 payments, right? And each payment was for $1,532.92. That comes out to $551,851.20. So that's a lot of money, right? That's almost like well, not double, but it's like about $2,000 and some dollars more. I mean, $200,000 more. Let's see the exact value. So you end up paying this much for your house. A house that was worth $325,000, you end up paying like $551,000, almost $552,000. Let's see how much money in interest you paid. So we subtract the $551,000 minus the original price. So you end up paying like $250,000 more for the house. But how can you avoid How can you avoid that? You can avoid that, but actually pay more money every month. So every payment that you can give extra, go ahead and give it. This way, it can begin to decrease the interest that you're paying in there. That's why I tell my students when they're going to buy a house, pay more than what the actual payments are. Pay more. If you can pay for 100 more, pay for 100 more. If you can pay 1,000 more, pay 1,000 more. And this way, the house will be paid much sooner than 30 years, and you will not end up paying all that interest. Okay. Hey guys, thank you for being a good crowd. If you have any questions, let me know. If you want a copy of this PowerPoint, send me a text at my email, and I'll be more than happy to send you a copy of this PowerPoint. Okay, let me go back.
Thank
so I
you,
can
Mr.
see.
Azasi. Is there any questions for Mr. Azasi today?